Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and we've done it again. We've got another great Hubble Hangout planned for you this week. Astronomers using the Hubble Space Telescope have generated the most accurate statistical description yet of faint early galaxies as they existed in the universe 500 million years after the Big Bang. And we're going to talk about these findings in just a little bit with some of the astronomers that have made these analyses public to us. But before I get started, I got something I want to say real quick. I just found this out yesterday. Now, sometimes before a Hubble Hangout, what I'll do is I'll go on Periscope and I'll do a Hubble Q&A, and I'll talk with you guys a little bit, maybe to get some people jazzed up about the Hangout. But it always ends up turning into a sort of a JWST Q&A more than that, because everybody's interested about the new mission and how it's coming up, how it's coming along. And everybody always, at some point, will ask me the same question. Aren't we worried about launching JWST out at the L2 point, and what if it gets hit by something, or what if something goes wrong with it? And it occurred to me yesterday that, you know, this is actually a solved problem. We solved this problem because when I first started my career in astronomy, I started in the solar physics area. And there is a spacecraft that we launched back in, let's see, December 2nd, 1995. And it was built by the Europeans and operated by the European Space Agency, but NASA had like 12 or 13 instruments on it as well. And they put it out at the L1 point, which is this point in between Earth and the Sun. We're going to put JWST at L2, which is 1 million miles away, and it's behind the Earth, so it's pretty far away. No repair missions were planned. It's been up there for 9 years, 9 months, and 29 days. But more than that, it's been sitting, like I said, at the L1 point, where it's in between the Sun and the Earth, where it is getting bombarded by coronal mass ejections on a regular basis while it measures and looks at the Sun. It has a lot of instruments. It looks at the chromosphere and like iron 9, 12, and 13, something like that. It also has 3 coronagraphs on board, LASCO, C1, C2, and C3. Now, they don't use C1 very much, but C2 and C3, as I was poking around on their webpage today, just discovered, not observed, but discovered its 3,000th comet. So it has been up there for a long time. So there's a precedent for this. No repair missions. Now, Hubble's great. We spend every week talking to you about how great Hubble is. We're celebrating 25 years of Hubble being in orbit this year, which is an amazing feat. It's the longest space telescope to ever have done that. But SOHO, the Solar Heliospheric Observatory, has been up there, it will be there 10 years, 20 years, actually, because this is 2015. I'm sorry, I have that wrong. 19 years it's been up now. So 20 years this December, 5 years after the launch of Hubble Space Telescope, they launched SOHO. So next time you get all bent out of shape about JWST being at L2, think about that for a second, because I think this is more of a solved engineering problem than anything else. So I just had to get that out because, you know, I don't know about you.
Don't get bent out of shape. Uncle Tony said.
Okay, we got it, Tony. We got it.
All right, so let's get started with this week's Hangout. It was related to a previous conversation that we had, so I wanted to get that out. With me, as she is every week, always making fun of me, my colleague and friend, Dr. Carol Christian. She is the Hubble Space Telescope Outreach Project Scientist. Hi, Carol. Welcome back.
Hi.
Glad to see you're in good form again. Thank you so much.
Oh, you're so welcome.
Also joining us, as he does each week, is the eminent Scott Lewis, Internet Driver Extraordinaire. Hi, Scott. Welcome back.
Thank you, Tony. And honestly, to defend Carol, which I don't often do, it's far too easy to make fun of you.
That's very true.
So she's got to work. It's
low hanging fruit.
I am an easy target. Okay, yeah, that's all right. Payback is a you know what. So okay. All right, guys. I got you.
Always get it back.
I see how it's going to be.
But the thing is, you'll be 10 years off by the time it happens.
Yeah.
In December, you're going to be hearing all about SOHO. 20 years. Now, if I were their EPO, I'd be getting ready for a big party. But anyway. Okay, so as I mentioned, we're back to Hubble and using the Hubble data. Astronomers at UC Irvine and other places have been using Hubble data to, like I said, look at the earliest galaxies in the universe, which is way better than the sun, in my opinion, also way better than anything else. The subject I covet the most, early galaxies in the universe. And with me to talk about this is Dr. Steven Finkelstein. He is an astronomer at the University of Texas at Austin. Hi, Steve. Welcome back. This is like you're going to be a regular here on our Hangouts.
Yeah. How you doing, Tony?
You're really good. Thank you. And also joining me is Ketron Mitchell-Wynn. He is a PhD student at the UC Irvine. He was part of the study that came out in I guess it was earlier this month, right, Ketron?
That's right, yeah. Well, last month now.
It was a journal, Nature, what was it called? Nature Supplement or something like that?
Nature
Communications, that's what it was. Okay, so let's before we get to your actual observations and the results from them, let's take a step back and talk about something that the Hubble has been doing for quite a while, which is these surveys. So these are sort of designed observation programs that Hubble does periodically. They've been doing these with right now. The main one going on is called Frontier Fields. It's looking at 6 different areas of the sky. But before that, there was another one called Clash, and before that was one called Candles, which is the Cosmic Assembly Near Infrared Deep Extragalactic Legacy Survey. Somehow that just seems like they were trying to make that work. But anyway, that's it. Candles. That's what Candles is. And you guys use Candles data for the survey, right, Ketron?
Yeah, that's right.
Okay, so this wasn't a data set that was designed for it wasn't for you specifically to do this work, but you found that it was observations that sort of enabled your work, correct?
Yeah, we had to do this complex mosaicing technique called self-calibration. And yeah, the Candles data was collected in such a way to maximize, I think, the area. But for us, that's not necessarily what we want. But when we supplemented the Candles data with archive data, we had plenty to work with.
Oh, really? So you used also data from the archive as well. Okay, Steve, let me get you. Okay, why don't you describe Candles for us first? Can we start there?
Yeah, sure. So Candles, you already spelled out the acronym. It's a long acronym, but it's one of the largest, if not the largest, Hubble program ever. So back in the last decade, there was a big program called GOODS, which took optical imaging, so visible light that our eyes can see. It took those kind of images of a few regions of the sky and learned a lot of stuff about galaxies at sort of moderate redshifts from time, say, 2 to 10 billion years after the Big Bang. But if we want to go back closer to the Big Bang, we need to look in the near infrared, because the expansion of the universe has redshifted all of the ultraviolet and the visible light of those very distant galaxies completely out of the optical into the infrared. And so when the astronauts installed the Wide Field Camera 3 infrared camera on Hubble in 2009, one of the most obvious things to do was to go and try and do a similar survey in the near infrared. It does take a long time, so there was a special call for very long proposals called multi-cycle treasury programs, and one of the ones that was selected was Candles. You also mentioned Clash, which looked at lensing clusters, and also FAT, which looked at the Andromeda galaxy.
Right, we just had a recent hangout on, well, we've had hangouts on all of these, but yeah, so they're called multi-cycle treasury programs.
That's right, yeah. And so Candles, the program Candles looked at 5 different regions in the sky. Altogether, they're pretty small. They are about 1/5 of a square degree. So it's actually, if you added them all together, it's smaller than the area of the moon. But for extragalactic surveys, that's actually pretty huge. And so the survey is now done. The science is not done. We're still actively working on papers like this great paper that Ketron wrote. But yeah, we've been learning a lot of great stuff about the universe.
Oh, great. Okay, I am remiss, folks. As Steve was talking, it occurred to me that I have not told you that we want you to interact with us in this hangout. We want you to ask questions and leave comments, and you can do that in a variety of ways. Scott, if you're still around and I didn't lose you from laughing at me, could you please explain to our kind viewers how they may interact with us?
Absolutely. So the best and easiest way for you to interact with us is while you're live here on the bottom left screen on this stream is some yellow text that says that we are answering your questions live, which we are. So we have a Q&A app, and we're able to see any questions or comments you leave there. You can upvote ones that other people have left. And so if we see anything really interesting that we want to address, we can click it. It will timestamp it when we're answering that question. So for those of you who are not watching live, you can see when those are being answered. You can also interact with us on Twitter. So I'm live tweeting this from @Hubble Telescope using the hashtag Hubble Hangout. So please send us your questions and comments on Twitter using that, and I will be, if it's something really awesome, I'll retweet it, or we'll be responding to them on air. And make sure to follow us, because we're always putting out really interesting stuff there on Twitter, too. And follow us over on YouTube. We are Hubble Site Channel on YouTube, and we're also on Facebook, so we have an event up there on Facebook. And we're also on Instagram @OfficialHubble, and you can see some awesome pictures and visuals that we put up there.
Yes, that's great. And I have been remiss in getting some pictures up on Instagram, so thank you for reminding about that.
Oh, I got you covered.
Of course you do. That's why you're here. Yeah, you got my back. All right, thank you. All right, so let's get back to these. I want to talk a little bit more about these multi-cycle treasury programs. And Carol, I was just wondering, one of the things I've noticed with our Hangout trends is we do talk a lot about these various surveys. We talked about FAT before. We've talked about Frontier Fields many times, and of course now we're on Candles again. Is this kind of a trend, do you think, with using Hubble in this way, where we're kind of setting aside blocks of time for Hubble to do very specific, sort of larger scale observations?
Well, it's a balance. I mean, when Hubble was first launched, everybody wanted to use the observing time, and there were lots of little projects. And there are still many projects that only use a few orbits, because there's lots of interesting science. Like if you want to look at a specific exoplanet, or you want to look at a stellar population of a specific galaxy. But surveys also are important, and it's also important to look at many objects in a survey mode using the same instrumentation. And so the idea was that part of the time Hubble should be devoted to these multi-cycle treasury programs. The interesting thing about it is that the team is really responsible for the calibration, and also the data becomes available very quickly because it's such a large amount of data. So the team that proposes the observation gets first crack at it, but they have to calibrate it and then put it out there in the archive to use. And what's been found is that what the original team thought they were going to do, they do, but then lots of other science can be done because there are several fields that are looked at that are pretty much uniform and address either galaxies or like FAT, the Andromeda Galaxy. And so there's lots and lots of information in those observations that can tell us about all kinds of astrophysics. So they are very productive in terms of Hubble observations.
Yeah, it sounds like a really good use of Hubble time.
And the other thing is, like, it's kind of like we're always saying, okay, you know, Hubble won't live forever. It's been here 25 years. What do we have to do with Hubble? And when the Hubble project asked that of the community, they said, we want to do more surveys. So it's a response to the community interest as well.
Oh, really? I did not know. Well, that explains why there's so many lately, then. I don't recall in the early days of Hubble. Of course, I've not been around as long, but it seems to me like this is sort of a trend now. So it's good to know. So,
well, you know what it started with? Your favorite observation.
That's right, the Hubble Deep Field. The very first one.
Wait, Tony likes the deep field?
You want to get started on that? Let's talk about
No, okay, I'm sorry.
All right. I'll curb that, but I will, instead of talking about the Hubble Deep Field, we'll talk about the deepest galaxies that Hubble can see. So, which brings me to, and as Carol alluded to, this Candle survey was one of those things that had a lot of other science that could be done from it than what it was originally intended from. So, Ketrin, tell us a little bit about what your work was. I mean, you started a little bit talking about this mosaicing technique that you were doing, but tell us a little bit about how you started this and what the science was, the driver behind it.
Okay, I'll start how I started. I started working on it 2 years ago. So Candles has a lot of data in the near-infrared bands, camera 3D. And we want to have a lot of different ways of spinning between the optical and the infrared. So we wanted to make 5 or 6.
Okay, so we're getting. Are you guys hearing it being really broke up, or is it just me?
No, I can hear it too.
Yeah.
Okay. All right. Good. So it sounds like you're really breaking up, Ketrin. Can you? I don't know if there's a way to get on a wired connection or not, or what, but you're breaking up, and we can't understand what you're saying. Is there?
Yeah.
or you could perhaps try getting out of the Hangout and coming back in, or just trying to plug in an Ethernet if you've got it. I'm not sure if that's possible or not. So while you're doing that, so let me go to you, Steve. Do you have what can you tell us a little bit about your role in this research, and maybe if you happen to know some of the science drivers early on behind it?
Sure. Yeah. So the main thing we're after is how many galaxies are out there in the very distant universe. Really, how much light are they putting out? Because we want to know how something happens that's called reionization. And so reionization is the process where the gas that's in between galaxies, and the universe is filled with gas in between the galaxies, basically lost all their electrons. So if this gas is mostly hydrogen, which just has one electron when it's neutral, but nowadays if you go out and look at all that hydrogen gas between the galaxies, it's ionized. They've lost their electrons.
It's just a proton and a neutron then?
Just a proton.
Just a proton.
Just a bunch of protons, yeah. And so we think that happened, that process happened, so we know it had to happen early on because we could look pretty far back, even all the way out to a redshift of 6 or so, just a little over 1 billion years after the Big Bang, and everything is ionized. And we know from our theoretical understanding that it had to be neutral at some point. And so something had to ionize the gas, and this process is what we call reionization. And people have been debating back and forth for a long time about whether it was galaxies that produced the photons to do this, or perhaps supermassive black holes that are accreting lots of material and being very energetic.
In the now we're still talking about the early universe, right?
The early universe, yeah.
So there were black holes around even at this stage.
Well, so there's one at redshift 7. We found one at redshift 7, and we found several at redshift 6. But the current thinking is that there are not enough black holes, and so it must be galaxies. And so the other way to answer that question is count up the galaxies and see if there are enough. And this was one of the main goals of CANDLES. It's also a main goal of the Hubble Frontier Fields, is counting up all the galaxies you can see, and are they producing enough photons to actually do this reionization? And the answer is actually no.
Oh, really?
But if we extrapolate from what we see, so we measure the distribution of luminosities, and then we just start, it's basically a histogram of galaxy brightnesses. And it just gets cut off at some point because Hubble can't see that deep. But if we extrapolate that further down to where we think galaxies may exist, what simulations tell us, it is enough. But we would like to observe them because simulations have been wrong before, right? It's just a prediction. So that's what Ketron has been doing.
So you really want to see them, not just infer that they're there.
We really want to see them, and so we're seeing some of them with the frontier fields. We'll see even more with JWST. We'll see even more with a JWST Frontier Fields program.
Ooh.
Even more, I don't know if you guys ever talk about the high definition space telescope. If you've had a hangout on that.
We're going to be doing that a lot more as time goes on. We've had one hangout on that already.
Yeah.
In other forum, but yeah. I want to. This idea of reionization is a very, very interesting one to me. And I'm going to oversimplify it, but it is a stage in the history of the universe where hydrogen atoms that were once had all of their it was basically permeated most of the dominant matter in the universe, lost that electron due to some mechanism. You're saying that it could be black holes, but there probably wasn't enough, and it might be the galaxies, but now you're saying probably not that either.
Well,
am I saying that right?
We think it probably is the galaxies. Well, we can't see the galaxies that are doing it.
I see. So that may be a limitation of Hubble.
Yeah, so there are way more galaxies we can't see than we can see.
Okay.
That being said, there was actually another recent papers that came out of CANDLES, combining CANDLES with Chandra X-ray data to show that perhaps there are a lot more quasars at higher redshift than we think, and maybe quasars could do it all.
Okay.
So that's very recent that paper came out.
Quasars in the early universe. So and what's the rough? So is the time period for this reionization like what the history of this particular research paper around 500 million years after the Big Bang? Is that the kind of time scale we're talking about here?
Yeah. So it was probably, we don't know, but it was probably a process that took a few 100 million years. And so our best constraints are reionization started, maybe between redshift 10 and 12 and ended at redshift 6.
Okay, so there is this need then to count as many as we can of the galaxies that existed in this period of the universe's history, to determine if they were responsible for, could have the energy enough to strip away these electrons from the early hydrogen atoms. And this sounds like and you're using Hubble to do it with candles, among other things. I wanted to talk to Ketron about the method that he used with it, but he hasn't returned yet. Is that something you could comment on?
I can briefly comment on it. He will do a much better job than I will, so I will hope he's plugging in his Ethernet cable as we speak.
Oh, okay.
Yeah, so what he's trying to do, I know you guys had that graphic you popped up a little bit ago, those blue and red images. So if you take, all the galaxies that are below the quote Hubble detection limit, we can't resolve them, we can't see them. Hubble is actually still getting light from those galaxies. There's just a lot of noise in there. But those galaxies are distributed about the universe, not in a random way, but in a clustered way. Galaxies like to live where other galaxies like to live. Galaxies cluster. And so if you try to statistically look at the background and see if there's any kind of preferential clustering of the fluctuations of the background light in the image, you may be able to get a handle on what's left. And so they take something like the candles image and remove all of the actual galaxies that we can see and try and see what's left, essentially.
Okay, so what are we looking at here? We've got 3 panels.
Yeah, and so we should ask Ketron again when he gets online. But the left panel, the left blue one is the actual candles image, and then the 2 right panels are 2 components of what is left after you take out the galaxy. So all those little white dots in the left image, you can remove them, or you at the very least you mask them out. That's actually what the holes are in the middle and the right panel.
Right.
You can see how some of those dark holes correspond to some of the big sources. So you just mask those out. You say, I don't have any information here. It's all blocked out by a nearby galaxy.
And then you really just pump up what's left.
Yeah, and so it turns out there are 2 components. The middle component was discovered, at least to my knowledge, or at least robustly discovered last year, where it was found that some of this background fluctuation is actually due to essentially homeless stars, so stars that have been stripped out of their galaxies due to gravitational encounters. Those kind of free-floating stars out there in the universe. But what Ketron was able to do with candles, with the unique wavelength range and depth probed by candles, was show that there was a second component from galaxies that had to be coming from the very early universe.
Okay, so
that's that right-hand panel.
Just to put a little bit of context here, this leftmost panel is a extremely teeny tiny little square of the sky. We're talking about a very tiny amount here. Good. He looks like he's back.
Yeah, sorry about that.
And that's quite all right. We can hear you much better now. I've got some more questions for you, and we're just kind of explaining what's going on. So this was what we're looking at in this panel, and Steve was giving us a little bit of background on what we're looking at. But I was just trying to get some context. This, when it says sky, we're looking at a real teeny tiny portion of the sky. So why don't you describe for us? I'd like to learn a little bit about what you did to sort of do this statistical analysis with this data. And Steve has already said that you've taken the stars here, and the ones that have been, when you call them tidally stripped, these are stars that are meant to be ripped away from their host galaxies. Mm-hmm. And what we're left with is what's in the center panel. And
right.
then you did something, and I missed it, about to get us to the right panel.
Yeah. So actually, both of those, the second and third panels, are both reconstructions, actually, of model fits that we did. So after I made mosaics in all.
Oh, wait a minute. So wait, you applied a model to what? The background of the leftmost image?
That's right. Yeah. So, well, a masked version of that sky. So after we removed all of the point sources, we isolated the background light, and the statistics comes in because we do what's called the angular power spectrum. It's very similar to what they did for the CMB.
That's a Fourier transform technique, right?
Yeah, exactly. Yeah.
Right.
Yeah. So on small areas, it's a Fourier transform. On larger areas, it's just a decomposition of the sky into the spherical harmonics.
Yeah. Okay. So and so this is a technique, folks, where if you have something that looks like a lot of noise, if there's any pattern in there, it'll come out in one of those kinds of transforms. So you did that.
We did that, and then we have a power spectrum measurement for all these different bands. And then Asantha and his postdoc applies these relatively complicated theoretical models, and they fit the data with their models.
Okay.
And so once they fit the data, they give me basically the model parameters, and then what I do is I invert the power spectra from those models back to real space, and you can see in the second and third figures what.
Oh, and then you
What it
count
would look
up.
like.
Okay. Oh, I get it now. All right. So you start with the background image of the sky and candles. We get rid of the stars. You do a Fourier transform or power, get a power spectrum of it. You apply a model which says, look, if your power spectrum looks like this, then you have this many galaxies in it, and your galaxy model will look like what I say. And then you took that model and said, okay, good. Well, this is what we have. The power spectrum does look like this model. Let me invert it back into space, and I will show you. And there's the galaxies, and then you count them all up.
That's right. Yeah.
Okay. So.
And that whole process took 2 years.
And that whole, but that's still really cool. I mean, I like that. So that is how. Okay. So this is stuff that's down in the noise of an image. When you talk about a background of an image, this is stuff where everything is like, you don't know if you're looking at noise from the sky or from the instrument or from Hubble or from whatever, or if you're looking at actual signal. Did you get that from the Fourier transform? Is that how
you... Well, we're looking at correlations. So a lot of the noise is uncorrelated. So what I did is I made...
Well, you're going to have to describe what you mean by that. What do you mean the noise is uncorrelated with what?
With itself. So
noise is not correlated with itself. That's the definition.
So meta.
Yeah.
So what I did is I made 2 different images of the same area of sky for each filter. So what I would do is I would take one image that has the exact same sky area as the other, like to the pixel, they're aligned.
But different filters.
Same filter or different filter, but let's just talk about the auto power spectra. So for the same filter, I would make 2 maps, and if I took the power spectrum of those 2 maps together, then what would happen is that the uncorrelated noise would drop out of it.
Okay.
If that makes sense.
Yes, I think. Well, enough. In a sense, enough. I think. So okay. So you were able, and that gives you obviously have some confidence level then in what you've got here.
Yeah, sure. So to get basically the noise power spectrum is I would subtract those 2 maps from each other, and that in principle would take out the astrophysical signal, and then I would take the power spectrum of that, and I would
get the galaxies.
And that would
the model.
Well, that would be our error bars, part of our error bars.
Oh, okay, good, awesome. Well, good. All right, so in a minute, I want to get to what your answer was and what you found after doing all of that. But Woot Vanderheid is asking, and Scott, if you wouldn't mind, I had asked you to grab a diagram for me that sort of shows the. Oh, you got something else up. What do you got up? Is that what it is? No. We'll come right back to that. But if I could get you to put up that map for me, or that diagram for me. He is asking, and I want to go back to this period of reionization because it's important. He's asking when and how did reionization occur? Now, this diagram kind of shows a history of the universe. This is one of my favorite kind of descriptions of the way in which things happened in the universe. So, Steve, can you give us some sense of where in this thing the reionization would lie?
I think I'm reading it right now. It looks like the second slice from the right, the kind of purple one, where sort of the first galaxies are forming.
So this part where it says structure formation, that's sort of what we're talking about here, and so we're looking, this is what, about 1 billion years or so after the Big Bang, and if you go backward, you see all kinds of very strange things happening, not the least of which is inflation, but that's a little outside of the order of this thing. But this is when we're talking about in the history of the universe, so about 1 billion, a little bit before that, years after the Big Bang. As far as how reionization occurred, that's what we're trying to figure out now, right, guys?
That's right.
So as Steve was saying, they thought that it could be due to black holes, could be doing this, but then there probably wasn't enough this early on in the universe's history, and now they're trying to determine if there are enough galaxies in the early universe to have had the energy to do this. And what Ketron's been doing is try to figure out, using these Fourier analysis techniques and modeling, how many there were. So you've got your error bars, Ketron. You figured out. You probably got a pretty good idea of in your little slice of sky there. How many galaxies did you find? Well, so what'd you find out? How many are there enough galaxies? Do you think to do this kind of reionization? And how many are there?
Yes, there are enough. We found that there are an order of 10 times as many as we previously thought.
10 times more galaxies than what everybody thought before.
Yeah. So a typical deep survey for Hubble usually takes really long integrations over a smaller area, and what they pick up is really the brightest sources at these really old epochs. But what we're doing is picking up a signal from kind of the more characteristic population. That's not as bright.
So is what Scott's showing now describing that? What is this showing actually? I don't get it.
Yeah. So this is the brightness of the background light as a function of wavelength. So the
wavelengths at the bottom and brightness. Okay.
Yeah, that's right. So the star formation rate is directly proportional to the amplitude of our power spectra, and that's shown with those yellow points. So the two rightward yellow points are the WIFC3 bands, and those are the two bands where we're picking up this high resolution. Yeah.
Yeah.
And then you go to the shorter bands, and the signal just totally drops out, and that doesn't contain any high redshift component in it. So based on the amplitude of that brightness, we can kind of deduce the amount of star formation that's going on.
Which tells you then how many galaxies there are.
Yeah, that's right.
I'm trying to get to the connection between the galaxies. What's that red line there? That just peaks at the near infrared. What's the wave? I can't see because everybody's thumbnails. What's the wavelength?
Yeah. That's right around 1 micron.
Oh, those are microns. Okay.
It's right above 1 micron.
Okay, good. So it peaks right around 1 micron, and so this is where Candles was giving you a lot of data. You said you also used archive data for this as well?
Yeah, I did. So Steve mentioned the GOODS survey. So that's
the survey before Candles.
Yeah, that's right. I think in 2004, Gia Velisco had a lot of observations in the Advanced Camera for Survey, the ACS instrument on Hubble. So what actually happened, I think on the 4th servicing mission of Hubble, they replaced the readout box for ACS, and that introduced some correlated noise into the instrument. So we actually couldn't use that much Candles data from ACS because of that. So we had to use archive data. And we used the majority of the ACS data is from the archive, from between 2001 and 2011, I think.
Okay. All right, so you found 10 times more galaxies than were previously thought in this period of the universe. You think there's more than enough now to understand the, I don't know if I should say the engine of reionization or not, but something that at least there's a driver behind some of it at least. Would it be helpful to go back any further than this particular period that Candles was looking at? Or is this pretty much as far back as you need to go? And by far back, I mean, yeah, cosmologically, earlier in the universe. Is this about would it help to go any further back?
Well, if we could, we would.
And why can't you?
Well,
right? Right. So, but you know, you see where I'm going with this. You've pretty much reached the limit of where Hubble can, at least in terms of Candles, can do. Carolyn,
they haven't got funding for their TARDIS yet. So they're waiting.
Exactly. So, I mean, Carol, I don't know if you know this or not, but is it possible to do anything more with this, do you think, with the Frontier Fields? Because Frontier Fields is cheating a little bit. Frontier Fields is using lenses, galaxy lenses, to kind of boost the power of Hubble. Is there a chance you think maybe this
by cheating you mean sciencing?
I think our guests are better suited to answer.
Sure,
but
sure.
The thing is that, yeah, it looks back. Part of the thing, I mean, for me, thinking about the Frontier Fields data, you've got this lensing stuff going on. So talking about how you're going to handle the instrumentation and how you're going to subtract out the lens galaxies and then the behind galaxies and see what noise you have left. I would think it would be possible, but you.
Yeah. What do you think?
Good lens models to do that.
What do you think, Ketrin? Do you think
maybe Ketrin and Steve are less shy than I am about that kind of data?
Does that complicate things? Having to undo the lensing models with Frontier Fields, would that help you at all, or no?
Well, I think that's a fundamentally different technique than what we're doing here, but people do that. Yeah.
Okay. All right. So probably not is basically it. So
Well, I think the bigger issue there, and Ketron can correct me if I'm wrong, is that the area that you get for each frontier fields cluster is much smaller than one of the candles fields, and so you would basically you're going a little deeper, but I think it's not really adding that much area, and then you have to mask out everything that's in the image, and there's a lot more galaxies in an image of a galaxy cluster than in the candles field. And so not only are you starting from a smaller image, you then have to mask a bunch of it out, and so you're just losing a bunch of space. You're losing more pixels.
Okay, so candles really was the ideal data set to help with this kind of research then, not so much.
I think you kind of need an unobstructed view, and that's why telescopes like JWST and the High Definition Space Telescope are of interest, because if you want to keep picking away at this problem, down at this level of noise, you really need more powerful, bigger telescope and more powerful instruments.
I'm so happy you went there, Carol. So let's talk about that for a second. Ketron, can you comment on that just a little bit? I mean, so we've done a lot of work with Hubble, about as much as Hubble can do with this kind of research, with finding these early galaxies. In what way does it help? Let me ask you this. I know JWST is probably going to be able to help in this way, but in what way are you helping JWST? I want to start there first.
Directly or indirectly?
Well, indirectly. I mean, aren't you kind of setting the stage for the signatures and the early work that if you push JWST, for example, like you do Hubble, and you use this technique, you can help JWST a little bit with its maybe pushing the boundaries a little bit. Am I wrong?
Yeah, hopefully. I hope that's the case, yeah.
Okay.
Maybe they'll be inclined to accept proposals with this kind of observation pattern.
Oh, I see. Okay, good. So, and of course, then the next question is JWST going to help with this?
Oh, absolutely, yeah.
So,
there's a chance that they could even resolve these individual galaxies, but...
Yeah, because right now, what you're looking at in noise, or in background, I shouldn't call it noise, is JWST might actually be able to resolve, correct?
Yeah, so everything I do is unresolved. It's just blobs of over and under densities.
Right, that's an important point, because you're relying on these power spectra to point out the features of these things for you, and to identify them in these models to sort of unravel what you're looking at. But here, JWST will actually provide observations, correct?
Yeah, and the resolution and the sensitivity is going to be so much higher that they might even resolve them individually.
And then, of course, after that, we've got even bigger HDST, as Carol pointed out, coming at us. What about W first, Carol? Do you think
that's what Steve was talking about? Is that you picking away at this problem, and then So I think what's being said here is that you can infer that those objects exist, but you really want to see them.
That's right. That's a good point. So right now we're inferring, based on power spectra, that they're there, and models that suggest, they should be there, but we haven't actually put our fingers on them yet and said, yes, there's one.
And that's where the frontier fields can help out. They're not going to see them all, but we're working on the frontier fields in my group, and we're finding a lot of very, very faint galaxies that are fainter than Hubble was able to see before. So maybe we can do another hangout on that sometime.
Of course.
Write that paper.
We haven't done a frontier fields one in a while, so yes, I'd definitely like to talk a little bit more about what's going on there. So that's great. That's great news. Okay.
W first. You mentioned W first. W first would also be very useful for these types of analyses, because it's got very wide fields.
That's right. Good. I'm glad because that's going to be the reason I wanted to bring it up was because that's going to be before HDST. So, W first will be able to contribute to this quite a bit, actually, I would imagine, because it can look at huge areas of the sky.
Yeah, absolutely. It can look at huge areas, but it's a Hubble-sized telescope. But a single picture with W first is something like 100 times the area of a single picture with Hubble.
So, Ketron, I know this is a loaded question, but you're a PhD, you're on track, you're a grad student, ready to become a PhD. Are you excited about using JWST and then following by W first? And are you going to be getting your PhD soon?
That's a terrible question. Are you getting your PhD soon?
That's not a terrible question. Are you on track? Are you?
Yeah, actually, I think I'll probably get it.
About it.
Next year.
We're gonna mute you if you're not. So
I'm gonna refer you to PhD comics and things you should not ask a grad student.
I said it was a loaded question, and I did not mean it in any other way other than the way I said it. So good. Well, that's so good because you're the generation of astronomers. I point this out because you're the generation of astronomers for which JWST is prime suited to help, and I just wanted to know what your thoughts are on the possibilities of using a telescope like that.
Yeah, I mean it would be very amazing if I had the opportunity. But I guess it's a few years away.
2018. Yeah. So you've got time. See, you're no hurry. You got time to finish.
Yeah, I'll probably finish before that, and hopefully there are postdoc opportunities that would allow such a study.
Good. All right. Well, that's good to know, and I wish you best of luck in the course of your research. And this particular result is, I find, a very fascinating one. So I want to thank you for taking the time out to talk to us about this. Let me look and see if I can find any. The Q&A app just to go. Oh, evening Hubble huggers. Yes. Good evening Hubble huggers, or good afternoon, depending on your time.
Well,
slot.
I had a question in trying to understand the way that the data is handled. So, are you having to deal with a lot of calibration and instrument effects to make absolutely sure that what you are seeing is a real signature from an astrophysical, density of astrophysical objects? I mean, it seems like when you work around in the noise like that, it's very difficult.
Yeah, that's a good question.
How do you know?
Well, we do simulations.
Okay.
So we have a huge collection of these raw individual exposures, which make up a small subsection of the whole mosaic.
Oh, okay.
So what I'll do is I'll inject some signal into these individual frames, a signal that I know very well, and then I'll mosaic them, and then I will see how well my mosaicing routine is removing offsets and things like this, and then I'll take that into consideration with the final power spectra and add the error. The total error budget is also a function of those simulations. So I spent probably 4 or 5 months just running simulations to kind of quantify the noise and get a hold on the different errors.
So, I mean, I think this is an important point about the way that, you just don't take in an observation and voila, you have this amazing result, is that there's getting the data, calibrating it, make sure it's the best data, you can clean it as best you can. Then you have the modeling, which is trying to look at what the astrophysics underlying. And then, in a lot of things, you do simulations where you put a known thing in, you see if you can get back out, and that kind of thing. I think it's interesting that shows up in many different areas of astrophysics in trying to understand the data that comes out.
Yeah. And also what I was talking about before, how I had 2 images for each field, for each filter. So when I subtract those 2 images from each other, the astrophysical signal should go away, and it does. It should, and it does. Yeah.
Well, that's good. That's good.
That's good. But it is a very long process from the initial exposure to the final results.
All right, got a dark. Go ahead, Carol. Are you done?
Oh, well, I had one other question in trying to understand. So if you tried to do this with one field, it would be a little more, I would think, I don't know, would be a little more difficult. But the fact that you have these mosaics and that you have several data sets allows you to understand the instrument better. Then it seems like the instrument, you would be able to understand the signature of the instrument itself pretty well, so that you're not being fooled by some funny effect from the instrument.
Right.
And you had mentioned ACS, right? That there was a change, and then it wasn't so forward.
Yeah, there's this Eureka package that a big group of smart people at Space Telescope are writing.
That's right.
Which, I mean, it's really amazing because they're basically doing all of the hard work. They're finding all of these things that you're talking about, the instrumental effects, and finding ways to kind of ameliorate all of the different things that could go on. So I'm just running Python scripts that call these functions that people smarter than me have already written.
That's right. That's a big effort here at the Institute. It's called Eureka, Ureka, and it's a really important astronomy software package for people who use Hubble data. So I'm glad you gave the shout out. I'm sure they'll appreciate it.
I was using it today earlier. Not even for Hubble data.
Yeah.
Another endorsement. Oh, good. They'll be happy to hear. That's done with our science software branch here at the Institute, so that's really great. I have a dark matter question from Michael Jobin. Hi, Michael. Welcome back. I'm always glad to see your questions. He wants to know, how do we know dark matter is as a kind of particle only, or not just some bodies of some sort that we can't see yet? But you want to comment on that, Steve, maybe? Or is it how do we know it's a particle?
I saw that question a minute ago, and I was like, oh, that's a really good question. So
yeah, we always give good questions on this.
Particle physicists will provide a much better answer, but I will provide an astrophysical answer, which is we can see that the densities of the centers of galaxies are really high, and this is just a guess, but I'm guessing that if it was due to actual regular matter, like say a bunch of asteroids or something like that, there would have to be so many that either A, you would see them, or B, they would prevent things from moving around in their orbits. So stars and other things would be smashing into it all the time. And that would cause things to glow, and we would see it.
Good question.
So that is an answer. There are probably better answers.
That's right. There's a lot about dark matter we're still trying to find out. So according to the press release I was just reading here, and the next area open that follows from what you guys are doing is that you want to kind of look in the X-rays next to see what's going on with some of this primordial stuff that's out there, because the earliest stars, they were very large and they collapsed really quickly because they were so large, and so they did this thing called I forget the name now. Is it core collapse? I forget the kind of supernova it was. It was a very special kind. Anyway, and those would show up in the X-rays. So are there any plans for you guys to be doing some X-ray work, or is that other members of the team?
I actually just sent a draft around about X-ray cross correlations yesterday to the collaborators. So yeah, we are doing that. We are cross-correlating X-ray background maps with the maps that I made in Hubble. So the idea is that if there's a black hole signature in the really early universe, they would leave imprints on the cosmic infrared background, which is what we have maps of. So if we cross-correlate maps between the near-infrared and the X-ray, then if there's a strong correlation, that kind of hints that maybe the possibility is true.
Oh boy, this is one of those moments where it just hit me. Of course, there would be a background infrared map. All I ever we always think about is microwave background. We always think about that. But this infrared map, is it a whole sky thing, or is it most of the sky, or?
No, it's what we've been talking about. It's the Hubble maps.
Hubble maps. The whole cluster, the whole candles field, then the whole cluster survey.
Well, after all of the work that I did to try to get mosaics in all the fields, I can only do it in 2 fields.
Okay.
Because it's kind of a data constraint. But yeah, basically just cross-correlating with the maps that I already have from the work that I did in this paper. I can just cross-correlate with X-ray maps and investigate that.
Very good. Okay, well, that's great. All right, well, I don't know if there's any other questions. Scott, is there anything I'm missing on Twitter? Anything you want to point out, or we good to go?
No, I think we're pretty good, actually.
Okay, all right. All right, folks, well, I guess that'll do it this week. Next week, we have a hangout planned for you that I'm going to have. Carol, I don't get what it says. AUMIC. Can you describe what that what that is? What do we got next week?
AUMIC is well. I also want to say NASA is pushing a little bit in October. The exoplanet research. There's also the Division of Planetary Science having a meeting and all that. So AUMIC was known to is an exoplanet system. It is known to have a disk, and it has been observed both by Hubble and other instrumentation, and seems to have some funny things about the disk. And so we're going to talk with the authors about how they use the Hubble data and what they are learning about this disk. This one it's not like, oh, it has a disk. It's known to have a debris disk. And so it's like they're now kind of looking at it and seeing. This is another case also of using multiple telescopes, observing something over a period of time. So it shows why that kind of research is worthwhile. So it's basically about an exoplanet.
and that is next week, folks. So I hope you'll join us. I want to thank you guys for. I want to thank our guest, Ketrin Mitchell-Wynn. He's from UC Irvine. Thank you so much for taking the time out to talk to us about your research. This is awesome stuff, and I hope you'll come back after you do the X-ray stuff and follow up. Okay, and good luck to you.
Tony.
And good luck to you.
Right.
Thanks and Dr. Stephen Finkelstein. He's also the astronomer from University of Texas at Austin. Thank you, Steve, for coming back. It's always great to have you on our Hangouts.
And he's going to be back with us at the end of the month. So.
Well, I didn't look that far ahead. Is that true? Great. Outstanding. Well, I look forward to talking to you again, Steve.
Absolutely. It'll be good.
All right. All right, Carol, Scott, thank you very much. That's it for this.
All.
Yeah, thank you. That's it for this week's folks. Thank you all for watching, and as always, and don't forget about Soho. I'm telling you.
Don't forget about Soho.
That's right. 20 years. No.
Forgetting about Soho was a no-no.
Yeah. Soho, no.
We'll never hear the end of it.
Don't be a Soho, no. All right, that's it.
We're done.
Bye-bye. We're done. Thank you all for watching.
See you next week, everyone.
Keep looking up.
3 infrared camera on Hubble in 2009, one of the most obvious things to do was to go and try and do a similar survey in the near infrared. It does take a long time, so there was a special call for very long proposals called multi-cycle treasury programs, and one of the ones that was selected was CANDLES. You also mentioned CLASH, which looked at lensing clusters, and also FAT, which looked at the Andromeda galaxy.
Right, we just had a recent hangout on, well, we've had hangouts on all of these, but yeah,
right.
So they're called multi-cycle treasury programs.
That's right, yeah. And so CANDLES, the program CANDLES looked at 5 different regions in the sky. Altogether, they're pretty small. They are about 1/5 of a square degree. So it's actually, if you added them all together, it's smaller than the area of the moon. But for extragalactic surveys, that's actually pretty huge. And so the survey is now done. The science is not done. We're still actively working on papers like this great paper that Ketron wrote. But yeah, we've been learning a lot of great stuff about the universe.
Oh, great. Okay, I am remiss, folks. As Steve was talking, it occurred to me that I have not told you that we want you to interact with us in this hangout. We want you to ask questions and leave comments, and you can do that in a variety of ways. Scott, if you're still around and I didn't lose you from laughing at me, could you please explain to our kind viewers how they may interact with us?
Absolutely. So the best and easiest way for you to interact with us is while you're live here on the bottom left screen on this stream is some yellow text that says that we are answering your questions live, which we are. So we have a Q&A app, and we're able to see any questions or comments you leave there. You can upvote ones that other people have left. And so if we see anything really interesting that we want to address, we can click it. It will timestamp it when we're answering that question. So for those of you who are not watching live, you can see when those are being answered. You can also interact with us on Twitter. So the
main one going on is called Frontier Fields. It's looking at 6 different areas of the sky. But before that, there was another one called Clash, and before that was one called Candles, which is the Cosmic Assembly Near Infrared Deep Extragalactic Legacy Survey. Somehow that just seems like they were trying to make that work. But anyway, that's it. Candles. That's what Candles is. And you guys use Candles data for the survey, right, Ketrin?
Yeah, that's right.
Okay, so this wasn't a data set that was designed for it wasn't for you specifically to do this work, but you found that it was observations that sort of enabled your work, correct?
Yeah, we had to do this complex mosaicing technique called self-calibration. And yeah, the CANDLES data was collected in such a way to maximize, I think, the area. But for us, that's not necessarily what we want. But when we supplemented the CANDLES data with archive data, we had plenty to work with.
Oh, really? So you used also data from the archive as well. Okay, Steve, let me get you. Okay, why don't you describe CANDLES for us first? Can we start there?
Yeah, sure. So CANDLES, you already spelled out the acronym. It's a longer acronym, but it's one of the largest, if not the largest, Hubble program ever. So back in the last decade, there was a big program called GOODS, which took optical imaging, so visible light that our eyes can see. It took those kind of images of a few regions of the sky and learned a lot of stuff about galaxies at sort of moderate redshifts from time, say, 2 to 10 billion years after the Big Bang. But if we want to go back closer to the Big Bang, we need to look in the near infrared, because the expansion of the universe has redshifted all of the ultraviolet and the visible light of those very distant galaxies completely out of the optical into the infrared. And so when the astronauts installed the wide field camera.
Welcome back.
Thank you, Tony. And honestly, to defend Carol, which I don't often do, it's far too easy to make fun of you.
That's very
true. So she's got to work. Just right.
It's low hanging fruit.
It's
I am an easy target. Okay. Yeah, that's all right. Payback is a you know what. So okay. All right, guys. I got you.
Always get it back.
I see how it's going to be.
But the thing is, you'll be 10 years off by the time it happens.
Yeah.
In December, you're going to be hearing all about SOHO. 20 years. Now, if I were their EPO, I'd be getting ready for a big party. But anyway. Okay, so as I mentioned, we're back to Hubble, and using the Hubble data. Astronomers at UC Irvine and other places have been using Hubble data to, like I said, look at the earliest galaxies in the universe, which is way better than the sun, in my opinion, also way better than anything else. The subject I covet the most, early galaxies in the universe. And with me to talk about this is Dr. Steven Finkelstein. He's an astronomer at the University of Texas at Austin. Hi, Steve. Welcome back. He says like you're going to be a regular here on our Hangouts.
Yeah. How you doing, Tony?
You're really good. Thank you. And also joining me is Ketron Mitchell-Wynn. He is a PhD student at the UC Irvine. He was part of the study that came out in I guess it was earlier this month, right, Ketron?
That's right, yeah. Well, last month now.
It was a journal, Nature, what was it called? Nature Supplement or something like that?
Communications.
Nature Communications, that's what it was. Okay, so let's take before we get to your actual observations and the results from them, let's take a step back and talk about something that the Hubble has been doing for quite a while, which is these surveys. So these are sort of designed observation programs that Hubble does periodically. They've been doing these with right now with the Earth, where it is getting bombarded by coronal mass ejections on a regular basis while it measures and looks at the sun. It has a lot of instruments. It looks at the chromosphere and like iron 9, 12, and 13, something like that. It also has 3 chronographs on board, LASCO, C1, C2, and C3. Now, they don't use C1 very much, but C2 and C3, I was poking around on their webpage today, just discovered, not observed, but discovered its 3,000th comet. So it has been up there for a long time. So there's a precedent for this. No repair missions. Now, Hubble's great. We spend every week talking about how great Hubble is. We're celebrating 25 years of Hubble being in orbit this year, which is an amazing feat. It's the longest space telescope to ever have done that. But SOHO, the Solar Heliospheric Observatory, has been up there, it will be there 10 years, 20 years actually, because this is 2015. I'm sorry, I have that wrong. 19 years it's been up now. So 20 years this December, 5 years after the launch of Hubble Space Telescope, they launched SOHO. So next time you get all bent out of shape about JWST being at L2, think about that for a second, because I think this is more of a solved engineering problem than anything else. So I just had to get that out because I don't know about you.
Don't get bent out of shape. Uncle Tony said.
Okay, we got it, Tony. We got it.
All right, so let's get started with this week's Hangout. It was related to a previous conversation that we had, so I wanted to get that out. With me, as she is every week, always making fun of me, my colleague and friend, Dr. Carol Christian. She is the Hubble Space Telescope Outreach Project Scientist. Hi, Carol. Welcome back.
Hi.
Glad to see you're in good form again. Thank you so much.
Oh, you're so welcome.
Also joining us, as he does each week, is the eminent Scott Lewis, Internet Driver Extraordinaire. Hi, Scott. Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and we've done it again. We've got another great Hubble Hangout planned for you this week. Astronomers using the Hubble Space Telescope have generated the most accurate statistical description yet of faint early galaxies as they existed in the universe 500 million years after the Big Bang. And we're going to talk about these findings in just a little bit with some of the astronomers that have made these analyses public to us. But before I get started, I got something I want to say real quick. I just found this out yesterday. Now, sometimes before a Hubble Hangout, what I'll do is I'll go on Periscope and I'll do a Hubble Q&A, and I'll talk with you guys a little bit, maybe to get some people jazzed up about the Hangout. But it always ends up turning into a sort of a JWST Q&A more than that, because everybody's interested about the new mission and how it's coming up, how it's coming along. And everybody always, at some point, will ask me the same question. Aren't we worried about launching JWST out at the L2 point, and what if it gets hit by something, or what if something goes wrong with it? And it occurred to me yesterday that, you know, this is actually a solved problem. We solved this problem because when I first started my career in astronomy, I started in the solar physics area. And there is a spacecraft that we launched back in, let's see, December 2nd, 1995. And it was built by the Europeans and operated by the European Space Agency, but NASA had like 12 or 13 instruments on it as well. And they put it out at the L1 point, which is this point in between Earth and the Sun. We're going to put JWST at L2, which is 1 million miles away, and it's behind the Earth, so it's it's pretty far away. No repair missions were planned. It's been up there for 9 years, 9 months, and 29 days. But more than that, it's been sitting, like I said, at the L1 point, where it's in between the Sun